Hello and good day everyone. In the last video, I've shown you how to add two fixed point numbers using the binary table which we have created in Google Sheet earlier. In this video, I'm going to show you how to use the same table in order to add two floating point numbers. Now the addition between fixed point and floating point numbers are not much difference, especially in a case where the exponents are the same. If they are not the same, we can just adjust the smaller exponent to make them the same, and we apply the same process used in fixed point addition. To summarize the process of adding two floating point numbers, we have the following steps. First, we compare if the two numbers have the same exponents. If they have the same exponents, we can just easily add the mantisas together because in algebra, we have the theorem x plus y, xy plus yz is equal to quantity x plus z times y. Y is our 2 to the e, especially referring to, or rather analogous to the 2 to exponent we used in floating point representation. So x and z are our two mantisas. We can add them together if the exponents are the same. If the two exponents are different, we deal with the one with the smaller exponent. We adjust that by floating the binary point of the mantissa to the left. Remember that every time we do that, we are just dividing it by 2 or incrementing our exponent by 1. So the smaller exponent is adjusted so that it equals the bigger exponent. We do that by floating the binary point of the mantissa to the left, each time incrementing the exponent by 1. When the two exponents are equal, we add the mantissas. Now, sometimes when an overflow occurs at the most significant bit, the binary point position is floated to the left and the exponent is incremented by 1. Because in floating point, there's no overflow. However, there will be an underflow if there's a less significant bit that is discarded because of the limitation of the number of bits for the mantissa, allocated for the mantissa. Now, in this video, I'm going to show you the case in which the two numbers have the same exponents. And I'm going to make another video to illustrate the point when the two numbers have the same exponents. Let us head over to our binary table. We are going to add these two numbers. Now, I have made a computation converting these uh, two floating point numbers with the following exponent and corresponding mantissas. The first number is equivalent to 35.8766875, and the second number is equivalent to 56.25, and we add them together. Our expected sum is 91.9375. Okay, we will compare that later. So let us do the addition or the conversion right away. Let us head over to our binary table, and as usual, we will copy that binary table to our solution sheet because we will start converting from here. And we know that mantissa is fractional, so we place it somewhere here, okay, so that we can see it without having to navigate through the table. Okay, so we'll just distribute this according to the bits. So we know that this is fractional, so we occupy the first space after, first cell after the binary point. So we have a 1 followed by 3 zeros, followed by 3 ones, followed by a 0, and a 1 1. Now this is easy to do, so that because the formulas have been set, and we know the mantissa to be equal to this. No? This is the mantissa of 35.687. Now let us copy again. Let us copy the binary table again. This time to compute for the second addend. Okay. We know our second addend to be this. So like the first number, we'll place it somewhere it's visible so that we don't have to navigate our worksheet every now and then. So we'll just copy this, starting at the binary point because we know that this is a mantissa. We have 1 1 1 followed by 4 zeros, followed by a 1 with 2 zeros. So we now know that the mantissa is 0.8. 70625. Now, let us copy this. Okay, let us copy. We will now place the numbers side by side. Okay, so that we can add them together. So this is the first number, and we know that the mantisa is equivalent to this. Okay, we'll just copy the value of this, like copying, and then okay, what's the table that we have? Should place it here, paste values, and then we will cut this. We just delete this. Okay, anyway, delete this row. First mantisa is this. Do Control C and then paste it here. The second mantisa is this. Paste the values, and we'll sum them so that we can counter check. But we can count. We can also compute the values later. We'll compute the sum. That's 1.1. We expect that to be the same value, and then we will copy the converted bits and we will add them one by one. These are the two pieces. We expect the answer to be 1.4. Let's go over to the least significant bit and then start our addition. 1 plus 0 is 1. 1 plus 0 is also 1. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0 is also 1. 1 plus 0 is 1. 0 plus 0 is 0. 0 plus 1 is 1. 0 plus 1 is 1. And 1 plus 1 is 0 with a carry of 1. Now this is called an overflow. We know that it is 1 point something because we know that the place value here is 1. And this is a 0.5. Okay, so this is 0.5 something. There's a slight difference because we only have a 10-bit mantisa. Now, since this is since this is there is an overflow, what we will do is we will copy this and shift the value to the right, or move. We will float the binary point to the left. Control Shift V. That's the shortcut for copy values only. Okay. Now we will move this over to the right so that we can place this one to that position. Okay, we'll have Control X this and we will Control V here. So now we have moved or shifted the position to the right, and we will put the one here and we will delete this. Okay, so now we have floated the binary point to the left. Okay, and let us copy our uh, our binary table again and find out what the equivalent number is. Okay, it's a very useful table, no? Because we will use this every time. And we will plug in the values, plug in these values, which is our mantisa, and find out what it is. Okay, is that correct? Have we plugged in the right values? Yes. I've copied this from the sum, and our new mantisa is here. It's 0.717. They're different because we have a different exponent. So our exponent, which used to be 6, is now 6 plus 1 because we have shifted or floated our binary position to the left. So once. So therefore, we are going to add 1 to our exponent. If you have shifted it twice, we will add it with 2. So therefore, our new exponent 7, which is now is 7. So we'll now have to compute for 2 to the 7. 2 to the 7 equals 2 exponent raised to the 7. Our new exponent multiplier is 1 to 8. Okay? And our mantisa is this. This is our new mantisa. We'll do a Control Shift B or P. Okay? And then we will multiply the mantisa with the exponent. So this is our decimal, the sum in our decimal value. Let us compare this to our expected sum. Okay. Our expected sum is 91.9375. Control Shift V, and we have 91.875. So they are more or less the same, except that we are using only a limited mantissa of 10 bits. If we will use a standard 23 bits, they could be closer because we will have smaller underflow. However, this illustrates the point that the floating point representation cannot have an overflow because we will, after an overflow, we are going to adjust the position of our floating point by our binary point by floating it to the left. Although we are losing accuracy, but still we are able to avoid the underflow. And underflows are further avoided by increasing the length of the mantissa, like 23 bits in the 32-bit flow of C or IEEE standard. So this is all about it. In the next video, I'm going to show you an example of adding of floating point numbers when they have different exponents. Thanks for watching and see you then.